So, hello everyone, my name is Jeremy Yang, and I'm here to present our work, CardiacNet, learning to reconstruct abnormality from cardiac disease assessment from Echocardiogram video. This project is a collaboration between Lin Yiqun, Pu Bin, Guo Jiarong, and Li Xiaonong from the Hong Kong University of Science and Technology, and Xu Xiaowei from Guangdong Provincial People's Hospital. So, echocardiography or cardiac ultrasound use ultrasound waves to create real-time videos of the heart, enabling us to visualize cardiac structures such as the ventricle and atrium, as well as assess their motions. This technology is essential for diagnosing cardiovascular disease, including congenital heart defect, pulmonary hypertension. However, existing echocardiography analysis methods face challenges when identifying subtle motion and structural abnormalities, which are crucial for detecting different types of cardiac disease. So, in this paper, we generally summarize that there exist two types of abnormality we deal with in the echocardiography. The first one is the structural abnormalities, where specific regions of the heart show visible structural issues. The second one is the motion abnormalities, where the structure may seem normal, but the cardiac movement reveals dysfunction. Existing datasets overlay the necessary resolution and diversity to effectively analyze both types of abnormalities. For example, public datasets like CAMERS and ECCV focus on only ejection fraction evaluation, and they are not able to capture subtle motion change or structural issue well. Hence, in order to enable the research in both structural and motion abnormalities, we collect two new benchmark datasets, namely CardiacNet ASD and CardiacNet PAH, specifically for assessing atrial septal defect, which is a typical congenital heart disease, and also the pulmonary arterial hypertension that reflects the cardiac motion dysfunction. Compared to the existing datasets, our dataset provides the high-resolution video, a wide range of the cardiac disease, including both structural and motion abnormalities. All previous echocardiographic datasets focus on only the ejection fraction evaluation. Instead, our datasets focus on specifically for cardiac disease assessment. This dataset can provide research with the opportunity to explore more detailed and accurate assessments of the cardiac conditions, both in structure and motion. Also, to address the limitation in existing methods, we propose CardiacNet, a novel deep learning framework designed for cardiac disease assessments. The key idea behind the CardiacNet is to moderate empirical knowledge of the cardiac anatomy. This allows our network to identify abnormalities even without annotation. So, for the overall pipeline of our CardiacNet, the bidirectional reconstruction design is a major pipeline. With the network A, reconstruct abnormalities for normal case, and the network B, recover structures from abnormal condition to normal. By simulating this deformation process, we capture detailed motion and structural change between two different groups. The core of each pipeline includes two modules, which are consistency deformation codebook that learns local structural abnormalities and motion change, as well as the consistency deformation discriminator that ensures the reconstructed videos remain spatially and temporally consistencies with the real one. This pipeline helps us assess cardiac conditions accurately and provides a more comprehensive understanding of disease progression. Now, let's look more closely at the one-way process of the bidirectional network. Here, we demonstrate how CardiacNet reconstructs an abnormal case from normal ones, using the consistencies deformation codebook to encode local features. We consider that a network understands the representation of a specific disease that can also reconstruct normal from abnormal or is in reverse process. Moreover, the cardiac structures remain the same across different patients or different cases. The spatial and temporal patterns should also remain consistencies. With such simple pure knowledge, we decouple the echocardiogram video to several patches, and for each patch, we utilize the code boot to capture essential characteristics of cardiac abnormalities by quantizing the feature space into distinct entries, maintaining both spatial and temporal consistencies in the reconstructed result. So in the next step, we focus on the consistency deformation discriminator. The role of the consistency deformation discriminator is to act as a discriminative network to compare the real case with the reconstruction result. This ensures that the spatial and temporal patterns of the reconstructed case match those of the real abnormal case and normal case. The consistencies deformation code book and consistencies deformation discriminator together enforce spatial temporal consistency during the reconstruction process, enabling our model to generate high quality abnormality reconstructions, and also ensure that the abnormalities are captured accurately, both in local regions and across the entire video. In this slide, we visualize how quantitative features are processed, use the memory bank to capture the distinctive characteristic of the normal and the abnormal case. Since it is impossible to compute all cases in only one step, we store the quantized features of normal and abnormal cases in memory bank, respectively, as approximate the overall distribution. Then we consider to optimize their transport distance between them. This approach helps in distinguish these two distributions more effectively, guarantee that our network can learn the representations from the overall data instead of focusing on only few cases. The visualization also shows the clear separation between the learned embedding of normal and abnormal cases, further highlighting the effectiveness of our methods. So in our experiment, we evaluated the CardiacNet using both our newly developed datasets and public datasets, cameras, and ECONET, and we are able to achieve the promising results. For example, in assessing pulmonary arterial hypertension and arterial spectral defect, the CardiacNet outperformed previous model with a clear margin. For the task of the ejection fraction precision, CardiacNet reduced error by almost 5.2% comparing to the pure methods. Additionally, the FID score indicating that our reconstructed video were more realistic and closely aligned with the actual patient data. And our ablation studies shows the design of both consistencies deformation code book and consistency deformation discriminator can effectively contribute to the CardiacNet. Furthermore, the CardiacNet enabled the visualization of the cardiac abnormalities. So, in the last, compared to the other methods, our reconstruction results can accurately find the abnormalities and reconstruct them correctly. That's all of our work, and thank you for your time and attention. The code and dataset are available on GitHub now. Our poster will available at 154. Please feel free to discuss with us. So we are happy to take any questions you might have. Thank you very much.
Thanks for the presentation. Questions, please don't leave. I think there is still one talk after. If you have any question, please come forward.
Thank you so much for your presentation. So, congenital heart disease, actually many subcategories improve the cases. So, for example, like the single ventricle or maybe two ventricle cases, and then so many variations of the CHD. So, how your methods address such the different cases?
As you can see in our dataset, we only focus on two types of disease, which is the atrial septal defect and the pulmonary arterial hypertension. So these two data sets are annotated by the experts from the hospitals. And in our future world, we will further collaborate with those doctors, and potentially we will have more data sets that related to other diseases. So currently we only focus on 2 diseases, also including the heart failure that evaluated by the ejection fraction evaluations.
So, and maybe even with the same cases, when maybe it looks like very different across the gestational ages. So then your method is considered such gestational the ages.
You mean in one case, a patient who have 2 types of cardiac disease? In this situation, we have not considered such situation in our work because, as you know, that all of our cases are only annotated with the 1 type of disease and verified by doctors. So, which means in our data sets, one case only have 1 disease. So we cannot explore this case yet. So maybe in our future work we will do that. Okay. Thank you very much.
So the one more question is.
I think we need to start because we are running out of time now.
Yeah.
10 minutes only, and I think there is one presentation missing. So I invite you to talk to the speaker after in the poster session. And thanks again, the speaker.